Nicolaus Copernicus, born in 1473 in Torun, Poland, embarked on a journey that would fundamentally alter humanity's understanding of its place in the cosmos. His magnum opus, De revolutionibus orbium coelestium, on the revolutions of the heavenly spheres, published in 1543, ignited a scientific revolution. Before Copernicus, the prevailing cosmological model was the geocentric system, meticulously codified by Claudius Ptolemy in the 2nd century AD. This Ptolemaic model placed Earth firmly at the center of the universe. All celestial bodies, including the sun, moon, planets, and stars, were believed to orbit Earth in complex, crystalline spheres. For over 1400 years, this geocentric view dominated Western thought. It was deeply intertwined with philosophical and theological doctrines. The Earth, as God's special creation, naturally occupied the central, most important position. However, the Ptolemaic system was not without its challenges. While it could predict planetary positions with reasonable accuracy, it required an increasingly intricate array of epicycles, deferents, and equins. These mathematical constructs were necessary to explain the observed retrograde motion of planets. Planets sometimes appeared to move backward in the night sky. This complex machinery made the model cumbersome and aesthetically unsatisfying to many astronomers. Copernicus, a polymath with expertise in mathematics, astronomy, medicine, and canon law, was among those who sought a more elegant solution. He studied at the University of Krakow, then Bologna, Padua, and Ferrara, in Italy. During his time in Italy, he was exposed to Renaissance humanism and critical thinking. He began to question the established astronomical paradigms. His initial ideas about a heliocentric system started to form around the early 16th century. He was not the first to propose such a concept. Ancient Greek thinkers like Aristarchus of Samos had suggested it centuries earlier. However, Copernicus was the first to develop a comprehensive mathematical model. He posited that the sun, not the Earth, was the center of the universe. The Earth, along with the other planets, revolved around the sun. The moon, in turn, orbited the Earth. This simple shift had profound implications. Naturally explained the retrograde motion of planets as an optical illusion. This illusion arose from Earth's own orbital motion relative to other planets. It also provided a more coherent ordering of the planets based on their orbital periods. Copernicus circulated an outline of his theory, known as the Commentarius, little commentary, among a few close friends and colleagues around 1514. This short manuscript contained the fundamental principles of his heliocentric system. Despite developing his full theory over decades, he hesitated to publish his complete work. He feared the controversy it might stir among both astronomers and theologians. The idea of a moving Earth contradicted common sense observations. It also challenged literal interpretations of certain biblical passages. For instance, Psalm 93:1 states, "The world is firmly established. It cannot be moved." It was only in the final years of his life, largely due to the encouragement of his young protege, Joachim Rheticus, that Copernicus finally agreed to publish De revolutionibus. Rheticus, a German mathematician, visited Copernicus in Frauenburg, now Frombork, Poland, in 1539. He spent 2 years studying with the master. Rheticus published his own account of Copernicus's theory, the Narratio Prima, first account, in 1540. This served as an important precursor to the full work. The printing of De Revolutionibus was overseen by Andreas Osiander, a Lutheran theologian. Osiander, without Copernicus's explicit permission, added an unsigned preface to the book. This preface controversially presented the heliocentric model as a mere mathematical hypothesis, not a physical reality, intended to soften the blow and avoid theological condemnation. De revolutionibus itself was a monumental work, divided into 6 books. Book I laid out the general vision of the heliocentric system. It included a mathematical exposition of the new order of the planets. Book 2 detailed the principles of spherical astronomy and provided a catalogue of stars. Book 3 focused on the Earth's motion, particularly its revolution around the Sun. Book 4 described the Moon's motion. Books 5 and 6I explained the motions of the other planets. Copernicus meticulously presented his arguments using geometric diagrams and mathematical calculations. He relied heavily on observational data, much of it inherited from ancient astronomers. He did not have access to telescopes, which would only be invented decades later. The book's immediate impact was not a sudden revolution. Instead, it was a slow burn. Many astronomers initially viewed it as a complex mathematical tool for calculation. They did not necessarily accept its physical reality. Osiander's preface certainly contributed to this initial reception. However, the book gradually gained traction among a small but influential group of astronomers. Its mathematical elegance and ability to simplify planetary motion were undeniable. Over time, as more precise observations became available, the heliocentric model proved to be superior in predictive power. The true Copernican revolution was not a single event, but a prolonged process. It unfolded over more than a century. Key figures like Tycho Brahe, Johannes Kepler, and Galileo Galilei built upon Copernicus's foundation. Tycho Brahe, a Danish astronomer, made incredibly accurate, naked-eye observations. These observations provided the empirical data that Kepler later used. Johannes Kepler, a German mathematician, used Tycho's data to formulate his 3 laws of planetary motion. These laws described elliptical orbits, not perfect circles, further refining the heliocentric model. Galileo Galilei, an Italian physicist and astronomer, used the newly invented telescope to make groundbreaking observations. His observations of the phases of Venus, the moons of Jupiter, and sunspots provided strong empirical evidence supporting the heliocentric view. Galileo's advocacy for the Copernican system, however, led him into direct conflict with the Catholic Church. The Church, adhering to the geocentric interpretation of Scripture and Aristotelian physics, deemed heliocentrism heretical. Galileo was tried by the Inquisition in 1633 and forced to recant his views. Despite this suppression, the scientific momentum generated by Copernicus's work was unstoppable. The shift from a geocentric to a heliocentric worldview was more than just a change in astronomical models. It represented a fundamental paradigm shift. It challenged anthropocentric views of the universe. It paved the way for a new era of scientific inquiry based on observation, mathematics, and reason. Isaac Newton, born in the year Galileo died, 1642, provided the ultimate theoretical framework for the Copernican system. His law of universal gravitation, published in Principia Mathematica in 1687, explained why the planets orbited the Sun. It provided a unified explanation for celestial and terrestrial mechanics. Newton's work solidified the heliocentric model as the correct description of the solar system. The legacy of De revolutionibus is immense. It marked the beginning of modern astronomy. It demonstrated the power of mathematical reasoning in understanding the natural world. It inspired generations of scientists to question established dogma. Copernicus's courage, even in posthumous publication, to challenge millennia of accepted wisdom, remains a testament to the scientific spirit. His book, initially a dense mathematical treatise, became a symbol of intellectual liberation. It moved the Earth from the center of the universe. In doing so, it moved the sun, metaphorically speaking, into its rightful place. The Copernican revolution was not merely about planetary orbits. It was about a new way of thinking. It was about the triumph of observation and reason over tradition and dogma. It reshaped not only astronomy, but also philosophy and theology. It laid the groundwork for the Enlightenment. The impact of his work continues to resonate in scientific thought today. Every time we launch a satellite or send a probe to another planet, we are building on the foundations laid by Copernicus. His quiet revolution, initiated by a single book, truly moved the world. The year 1543 stands as a pivotal moment in human intellectual history. It was a moment when humanity began to see itself, not as the static center, but as a dynamic part of a much larger, grander cosmic dance. This profound shift in perspective continues to inspire awe and wonder. It reminds us of the continuous quest for knowledge. The book's influence extended far beyond the realm of astronomy. It encouraged a critical approach to all forms of knowledge. It fostered a spirit of inquiry that characterized the scientific revolution. The meticulous calculations within its pages provided a new standard for scientific rigor. It was a slow but undeniable triumph of empirical evidence and mathematical elegance. The world would never look at the heavens the same way again. The Earth was no longer stationary. It was a planet among planets. This realization was both humbling and exhilarating. It opened up vast new possibilities for understanding the universe. The journey from Ptolemy to Copernicus was long and arduous. It required immense intellectual bravery. Book's publication was a quiet act of defiance. It set in motion a chain of events that would forever change science. The year 1543, therefore, represents a turning point. It is the year the sun truly began to move in the minds of men. The implications of this shift were felt across all intellectual disciplines. It was a testament to the power of a single idea. The book's title itself, On the Revolutions, foreshadowed the revolutionary impact it would have. It was a revolution not of violence, but of thought. The intellectual landscape of Europe was irrevocably altered. The scientific method gained prominence. The authority of ancient texts began to wane in the face of new observations. Copernicus, though hesitant, ultimately provided the spark. His work was a beacon for future generations of scientists. It taught humanity to look beyond appearances. It taught us to seek deeper truths. The heliocentric model, once a radical notion, became the cornerstone of modern astronomy. It was a testament to the enduring power of human curiosity. The book's journey from manuscript to print was fraught with challenges. Yet, its message ultimately prevailed. It was a victory for reason and observation. Year 1543 will always be remembered as the year the universe expanded in our minds. The Earth became a wanderer. The sun became the anchor. This reversal of roles was monumental. It forced a re-evaluation of everything. The book's impact was truly global. It transcended borders and cultures. It united humanity in a shared quest for cosmic understanding. The revolutions truly lived up to its name. It revolutionized our perception of reality. It was a quiet revolution with thunderous consequences. The scientific community slowly but surely embraced the new paradigm. The old ways of thinking gradually faded. The book's influence is still felt today. It is a reminder of the transformative power of scientific discovery. The year 1543 marked the dawn of a new scientific age. It was a bold step into the unknown. Book's arguments were compelling. They were based on careful observation and mathematical rigor. It was a masterpiece of scientific thought. The world owes a great debt to Copernicus. His vision changed everything. The book was a catalyst for change. It sparked a new era of exploration. The universe became a place of wonder and discovery. The Copernican model was a triumph of human intellect. It showed us the true scale of the cosmos. It was a humbling yet inspiring realization. The year 1543, a year of quiet revolution. The book's pages held the key to a new universe. It was a profound shift in human consciousness. The Earth's journey around the sun became a symbol of scientific progress. It was a testament to the power of challenging assumptions. The book's legacy is etched in the annals of science. It continues to inspire us to look up and wonder. The year 1543, a year that truly moved the sun.